So I'd like to talk about the cyclotron because it uses many of the concepts that we did last time. The cyclotron is an accelerator, and it's one of the first accelerators, and it was designed at Berkeley by Ernest Lawrence. He was the first one to do such a type of accelerator, and it was turned on in 1931. He received a Nobel Prize in 1939 for this accelerator and for the physics that he did with it. What is a cyclotron? Well, it brings charged particles to a very high velocity by using many small repeated accelerations. And that's done by E fields. Remember that magnetic fields alone cannot do work. So it's composed of a split hollow cylinder where each half is called a D because it's in the shape of a letter D. So here's a diagram of such a system. You have, here are the D's, and the split is right in the middle here like this. It's located between electromagnets. The electromagnets are built to try to achieve as uniform a B field in the region of where the D's are placed so that the orbits of the particles that are accelerated are as close to circles as possible. The acceleration is achieved by having an alternating voltage source. It says current here, but it's mostly voltage. And the electric field that is created by applying those voltages are designed so that it will give the particle a kick, so accelerate the particle. This particular diagram shows that as you reach the very outside of the D's, you have an extraction of the particle, usually with a little electric field that's applied, and so then it exits the D's and hits a target where you're going to do some nuclear physics. The basic idea then is that you continue to accelerate this particle, and then so at this point here it has a reasonably high velocity which you can then use. The other thing to realize is that you have to evacuate this system, and so the D's are inside of a vacuum system and also the flight path and where the target is located. The region above the electromagnets need not be evacuated. This is a diagram of an earlier version of the cyclotron. The original one, which is shown here in this picture, was approximately 14 centimeters in diameter, and that led to achieving a kinetic energy of about 40 keV. The original had this diameter here being about 5 inches, which is the 14 centimeters. So let's go through the equations for how this thing works. And for that, we'll let the y-axis be across the D's and the z-axis along the B0. This one shows a different extraction system, but here's the deflection electrode, and this happens to have a hole in one of the D's to let the particles out. Okay, so here again, the D's are driven by a periodic function or potential difference. It can either be a sine wave or a square wave. The advantage of a square wave is that you'd have constant potential during the time that it exists in the gap. So you'd have a better energy definition when you finally come out. So the spread in energies will be less. Okay, so the B field is perpendicular to the D's, and so that leads to circles that are in the plane of the D's in terms of the orbits. So in terms of the electric field is concentrated in the gap and is essentially zero inside the D's. In terms of the E field in the gap, we just take the potential difference between the two sides of the D's and the distance across the gap, and that gives us the E field. Now realize this is time dependent, so the E field is time dependent. And in this case here, it's in the y direction across the gap. So what you have is a source of particles here. It could be ionizing, for example, hydrogen gas, creating H+. There's lots of different ways of creating a charged particle. So it's emitted and has essentially zero velocity, and it's slightly accelerated the first time, and then we won't worry about that. And then every time it goes through the D, it's given a kick. So it's given a kick in this direction, it's given a kick in this direction because after it passes here and goes through here, the frequency of the oscillator is designed so that now you have a negative voltage, say, and this kicks it in this direction. Let's analyze in the gap. During the time that it's in the gap, the voltage is approximately constant, and so we'll set that equal to V0. While the charge is traveling between the D's, it's given a acceleration, and we can calculate, say, the velocity after it has gone through this displacement of S. So we start with Newton's laws, and it says that, of course, F equals ma, but what is the force? Well, it's equal to Q times E, and E is the electric field in the gap. So if we write down then what this is in terms of the potential and the S to get the E field, then the force on the particle electrically is this, and that's going to be equal to the change in the velocity with respect to time. This is A, of course. So times M. So then solve for V sub y by integrating this, and so we just get what we expect, Q over V0 divided by ms times the time t. But remember that the velocity is dy dt, so we can solve for y by just integrating again, and so y is equal to q v0 t squared over 2ms. So remember, t is the time that is passing as we go across the gap, where 0 is here and t is equal to t here. So let's relate that then to the parameters. So we have then that the time to go across the gap, let's say the first time, which we'll call t1, is equal to this quantity here. So assuming that the initial velocity is 0, and this gives us the result at t1. The velocity after passing through the gap the first time is given by the equation that we had just recently, and so that will be v1, and that's equal to this quantity here. So now we have basically the increase in speed of the particle because it was accelerated by v0 in the gap. So when d2 is, the electric field is equal to 0 within the d, so the charge travels, let's say for the first time inside d2, in a circular orbit of radius r1. Now remember that r1 is related to v1 divided by a parameter which is the omega, the frequency omega, which is related to the angular frequency and the circular motion that's happening in the d. Omega is, of course, related to the mass and charge in B, and so we get this expression here for R1, which we developed last time. So repeating the equation and getting very clear then that the omega is just a function of these parameters, I just want to remind you that we called this the cyclotron frequency, and that's where it came from. So we're anticipating this time where we identify omega sub c. And just to emphasize, this is a constant because all of these parameters are constants. It does not depend on the speed or velocity. It does not depend on the kinetic energy of the particle. Okay, so we have to match the frequency of the oscillating voltage, and so we either have a sine wave or a square wave, and the frequency will be 2 pi times f, which is the frequency of the oscillator. And this is adjusted so that the particle passes through the gap from d1 to d2, say, and so such that the E field is directed from d1 to d2 so that the particle is accelerated. Now it goes around and passes from d2 to d1, and what we want is that the sine wave or square wave has switched signs. So we're on the other half of the cycle. So there again, the E field accelerates the Q. Well, this goes on and on. The process is repeated, and so every time Q enters the gap, the E field accelerates the charge towards the opposite D. So the larger we get the velocity going, the larger the radius inside the D. So after n gap traversals, its velocity v sub n and the orbiting radius r sub n are given by these equations. And all we've done is put in n for the nth time that it's gone through a d, and this is the velocity that results. The r sub n has to increase because v sub n is larger. And so if we put in our equation for r, the v sub n, then we get this ratio. Well, we just determined this, and we know omega sub c, which is equal to this down here. So carrying out this division and simplifying, we get for the nth velocity, the nth time through the gap, this quantity right here. So if we consider this going on and on until we reach the outer radius of the d's, let's call it capital R, then we've basically achieved the maximum speed that we can of the charge. And so setting the V max equaling omega 0 times capital R, we end up with Q B0 over M, which is omega 0 times R. Don't forget that there's 2 times through the gap for every circle that we create. And so multiplying this in terms of the velocity, then this is equal to Q B0 squared R squared M over V0 round trips, and we're going to use this fact, and we just emphasize that here. The factor of 2 is needed because for a round trip the ion gets kicked twice. So let's put in the numbers. We have for the proton, we have the Q and we have the M. So Q is the charge of the electron except positive, and M is a measured number from previous studies, which is equal to 1.67 times 10 to the minus 27 kilograms. We'll take a B field of 1 Tesla, which is a fairly hefty magnetic field. Calculate omega sub c, and it comes out to be roughly 10 to the 8th radians per second. And the voltage that we're going to apply across the D's has a maximum of 100 volts. So then we put in our maximum velocity, which is 9.6 times 10 to the 7th meters per second. And if we compare that to the velocity of light, it's about 30%. So this is a particle that's moving fairly quickly. Well, the number of round trips, remember, was 2 times n max. And so we put that in to be 9.6 times 10 to the 5th round trips. The total time it takes to reach a radius of capital R is given by, first of all, this equation here, where 1 over f is the period to go around the circle once. So multiplying that by 2n max will give us the total time it takes. Putting in n max and f right here, we get this quantity here. Here's n max. Here's the angular frequency. And we calculate the time for the total trip to be 0.06 seconds. And here's the relation between omega c and the f. Well, this seems long, but realize that it's gone around a lot of times, basically 10 to the 6th round trips. From the relationship of the velocity, the Vmax, we can get the kinetic energy, which is 1/2 m Vmax squared. And so putting in the numbers, we get 7.7 times 10 to the minus 12 joules per proton. Now normally, instead of this unit, we use electron volts for the energy. And I'd just like to remind you how we get that. What we do is we set up a thought experiment where we're accelerating the particle from 0 kinetic energy at 0 volts potential to a voltage capital V, where we end up with V max. And we've already said that the kinetic energy will be equal to this in joules. So let's see how we convert joules to EV. And so we use a thought experiment where we basically have a linear accelerator. So we have these 2 grids or plates where we have this one at 0 volts and this one at capital V potential. So we'll start off with 0 kinetic energy here, and we're going to accelerate the particle up to V max by going across here. And remember that we've already determined the kinetic energy using the velocity, which is 1/2 mv max squared, and we set that equal to the energy that we would expect by going across v equaling q times v. So the kinetic energy in EV, and this is where we define it, is the voltage for this above accelerator to produce the kinetic energy in joules. So the kinetic energy in EV is just equal to the kinetic energy in joules divided by Q. And that comes from up here. We take kinetic energy, divide by Q, we get the capital V, which is equivalent to that. So in this case, the kinetic energy in EV is equal to this quantity, and we really should have down here the Q to equal this equation up here. And so when we put in the charge of the electron, positive, we convert that to EV, and it turns out to be 48 capital MeV million electron volts. So that's the way we do the calculation, and you probably learned this, but I wanted you to completely understand the thought process that gives you that number. We don't want to do this with electrons, and the reason is because it won't work. The small mass of the electron results in velocities that are relativistic, and so we're getting closer and closer to the speed of light. Well, what happens? The mass increases due to the relativistic equations. And so, as a result, if you look at the angular velocity, omega sub c, if the mass goes up, then we're going to be out of phase if we keep the omega sub c constant. So what happens then is the particle stops accelerating and basically no longer gives us a faster and faster electron. An early electron accelerator was called the Betatron, and you might want to look that up. For your information, the LHC, the Large Hadron Collector, which recently supposedly found the Higgs particle, has an accelerator energy of 7 capital TeV. Now remember that it's a collider, so it creates two particles going in opposite direction, and so therefore the energy of the collision is 14 TeV. Just to remind you, capital T is a tera, and that's 10 to the 12th. And so that's relativistic for any nuclear particle. Well, cyclotrons still are used even today, and the major application is isotope separation. So if you look at medical applications today, radioactive isotopes are frequently used. So how does that happen? Well, if you look at the omega sub c, remember it has m in the denominator here. And so if you're at different m, you basically go out of resonance. And so those particular masses, other than the one that you're selecting with omega sub c, don't make it through the cyclotron. So with special designs, in terms of keeping the frequency and the path very carefully designed, you can maximize the sensitivity to the mass, and so you can separate out the isotopes. The other thing to remember is that the cyclotron is not a pulsed accelerator, as all of the high energy accelerators today use pulses rather than just having them continuous. The cyclotron is a continuous current of ions. So what that means is that you get a larger yield, so the mass collected per unit time is higher, and so that is very attractive for this application. This is a picture of a commercial cyclotron. This happens to be used by RAD planning for isotope separation, and you can see the scale here by this stairway, that it's a fairly large instrument. And I would assume that this is the exit port here for collect the isotopes. Remember that the Ds at least have to be evacuated. I don't think this whole vessel is evacuated, but I may be wrong. So next time we're going to examine the forces on conductors and other systems due to magnetic fields.